Hello, everyone. My name is Oluyemi Aboyewa, and welcome to another lecture. Um, in this section, we'll be looking at the interaction of radio frequency wave with the human body. I believe so far we've been having interesting experience learning about the application of physics and engineering in medicine. And this topic is really exciting because the application of RF waves are ubiquitous. They are all around us. For instance, right now you're sitting in front of your laptop, listening to this lecture. These waves are interacting with your body, or probably you're making some phone calls that the wave is interacting with your body. So in essence, we want to know what are RF waves and how do they interact with the body. By way of motivating our discussion, here are two examples of people, societal perceptions about this wave. For instance, in 2019 in California, this is a news article from CBS News, where there were a lot of cancer cases among students in a particular school, and the parents linked that, filed a lawsuit against the telecommunication company because they believe it was due to the presence of their cell tower that was close to the school. Something to think about. In other recent events, there are a lot of conspiracy theories on Facebook, for instance, linking the latest 5G technology with the COVID-19 pandemic. So for us to be able to form a good opinion about some of the societal discourse, it is important for us to understand the physics of how radio frequency waves interact with the body. And that leads me to my study objectives. Basically, I will be talking about, we want to understand the propagation of RF waves through the body, and based on the energy absorbed by the body due to these waves, there will be a lot of safety considerations, things that we need to put in mind. And from our understanding of this physics, we can then apply that to medicine and see how we can use RF wave to our advantage. And I'll also talk about some possible areas of research. Now, I'd like to take a little bit of break, and I'm going to show us an introductory video that walks us through the electromagnetic spectrum. I will encourage us to pay attention to the video because it will build up our discussion that way. All right. Okay, interesting, isn't it? That we live in the sea of these waves and we're constantly bombarded by the waves, and one of that wave is the radio wave. So building up from the video,
sorry,
just as
sir. Sorry, were we supposed to hear or just see? Because we weren't hearing anything.
oh, I was expecting the sound to
Okay, well,
come.
it's okay. No problem. I just wanted to be sure I wasn't having the problem here.
Oh, I'm sorry about
Fine.
that.
All right, that's fine.
There was supposed to be an audio effect with that. Okay, I'll probably do most of the summary, but again, hopefully if you can connect some of what you see with what I'm going to say next. Now, I said just as mass is a fundamental, is just as the mass of an object, there are other fundamental properties of matter, and one of that is electric charge. Electric charge is also a fundamental property of matter, and these charges usually exert some influence around their surrounding. For instance, if I have a source charge and I bring another charge, which I call a test charge, in the vicinity of my source charge, that test charge is going to experience some influence due to the presence of this source charge. And that region of influence in which the presence of an electric charge is being felt is what we call the electric field. So simply put, we say that a charge will create some electric field around it that allows us, that tells us that the charge is present. Okay, and this electric field have some amount of energy stored in them. That is, if I'm going to be moving my test charge from different region within the field, I will have to do some amount of work. Okay, so keep that in mind. And now if I have my charges maybe oscillating or vibrating, I'm going to be creating some form of disturbance in that electric field. That is, we say charges produces electric field, but once my charges begin to oscillate and vibrate about some mean points, I create a disturbance in that electric field that can travel, that can transmit, that can propagate away from the source. Okay, and in our understanding of electromagnetism, when we have a spatial variation in this electric field, we create another thing. We create a time variation in some magnetic field. That is a consequence of Faraday's law. I hope some of us are familiar with that. And so we have this coupled effects where we have an electric field changing in space, leading to some temporal variation in magnetic field. Magnetic field are due to movement of charges or electrical currents, we say, and vice versa. So EM waves or electromagnetic radiation in essence are electrical and magnetic disturbances that can sustain each other and propagate in space. Like I mentioned, that the field has some amount of energy stored in them. That means this disturbance also carries energy with it as they move out away from the source. Now, one way to describe the amount of energy being transmitted is the word intensity. That is, we're looking at the energy divided by time until we have the power, and then moving away from the source, the power divided by some unit area, we call it the intensity. I'll use an example that I have, an illustration here. Say I have a point charge that is oscillating and creating some EM radiation, which is electrical and magnetic field disturbances. Uniformly in space, I would imagine that it is radiating into some hypothetical sphere, right? So the more I move away from the source, that is, I will intersect larger areas of this sphere. And in that sense, my intensity begins to reduce because my power is going to be constant by conservation of energy, but my intensity is going to reduce the farther I move away from the source. In that sense, we say that the intensity of an electromagnetic wave varies inversely as the squared distance from a source. Just think of it, power divided by area for an hypothetical sphere. In this case, as we're talking about, is just 4 pi r squared. In that sense, your intensity varies with the squared of the distance. For me to describe the motion of this wave and its temporal variation, I need some form of wave equation. And that wave equation can be gotten from Maxwell's equation that allows us to decouple the electric field component and the magnetic field component of this wave. All right. As shown in the video, which unfortunately we weren't able to hear the sound, various components of the electromagnetic field spectrum. And what do we mean by that? That is, depending on the frequency of oscillation of these electric charges, we have different forms of electromagnetic radiation, ranging from radio waves to gamma rays. I know during the course of this lecture, we have seen X-rays, we've heard about gamma rays, and our common visible light, which allows for optical sensation, is also within the spectrum. So radio waves are on the lower end of the electromagnetic spectrum, and they spread from about 30 kilohertz to 300 gigahertz. Okay, so because we have the frequency and we know the speed at which this wave propagates is the same speed of light, as mentioned in the previous lecture, 3 times 10 to the power of 8 meters per second, we can calculate the wavelength of this wave, which is just the distance between two crests. The distance between two crests on a particular wave will give us the wavelength, so we can calculate that wavelength. And for radio frequency wave, they're in the range of 10 kilometers to 1 millimeter. Now, besides the wave picture, there are other ways we can describe electromagnetic field radiation. We can think of it as composing some particles that carries these electromagnetic forces as they interact with material. And that particle concept is what we call photons. That is, they have some quantum amount of energy from this electric field that they can transfer to a given object. And in that case, we can describe the energy of an EM wave based on the frequency of the oscillation of the source times some constant, which we call Planck constant. And in this, for RF waves, we say that they are non-ionizing because by calculating their energy, they are in this range of electron volts, say 10 to the negative 3. For ionization, for instance, the first ionization potential energy of water is about 12.6 electron volts. So with radio frequency wave, we are really, really below that. And by ionization, what I mean is that we can, that is the process whereby the interaction of an EM wave detach electron away from some atom. Okay, so radio frequency wave cannot do that because its energy is really, really below the ionization energy of just adding some details to some of the radio frequency band. We have various applications looking at different range of frequencies within the radio frequency band that leads to some of the everyday applications, from our cell phone to our TV to satellite communication for GPS location, position locations and the likes. And that is ranging from low frequency to medium frequency and high frequency. All of these within the radio frequency band, we have different characterization and allows us to do some other applications as well. All right, so moving to an important aspect of this discussion would be to understand how RF wave couples with the human body. Now, generally, we've been hearing a lot about waves. Initially, we're talking about sound waves, and one of the properties of wave is that when wave interact with a material, it can either be scattered or is absorbed. By scattering, I mean the wave can be reflected. Take, for example, a wave moving towards the right, that is some disturbance carrying some amount of energy, electric and magnetic field energy, moving towards the right, can revert their direction when they come in contact with a material, that is, they can return moving towards the left, that is some reflection happening. Or the material can pass through, the wave can pass through a given material that it impinges on. In that sense, it's going to have some change in properties. For instance, its speed or the wavelength is going to change. Alternatively, the energy can be absorbed. That is, it is converted to some other form of energy. And at the end of the day, even if we're having a transmission, we don't have the full wave anymore. All right, but this interaction depends on the electrical properties of the material. Technically, we refer to this as some electrodynamic boundary conditions. Look at some of my illustration here, looking at various materials with different electrical properties. For a conductor, for a perfect conductor, we're going to have a total reflection. And that has some details to do with the electrical properties of conductors, because inside a conductor, we don't have any electric field, and most of the charges, because electrons have a lot of free charges, both positive and negative. It's just like a sea of electrons and positive charges. In that sense, they are well located around the surface, and it is their interaction with the EM field that causes that total reflection. This EM wave do not really penetrate into conductor. So technically, we describe that amount of penetration by some skin depth and the likes. But that is not the focus of our discussion. Looking at these classifications of materia, we see that human tissues are in the midline. That is, it has some properties of a conductor and some properties of insulators. And in that essence, part of this energy can be reflected, some portions can be absorbed, while others are transmitted or refracted through the material. And on the other end, for insulation, there are also some absorption as well. This is probably one of the busiest slides in this presentation with some equation, but I'm not going to be talking deep into any of this equation. This is just to allow us to see that there are ways in which we analyze and each of these components of the interaction of the wave with a material. So for instance, when we talk about reflection, like we mentioned, it can be handled by the laws of reflection. Let's say we have a smooth surface on which an electromagnetic wave impinges. By the law of reflection, we are saying that the angle of incidence and that of angle of reflection are the same. That is, if we look at some normal, a normal line perpendicular to the incident plane. And another thing when we're talking about refraction would be that, like I said, the properties of the wave is going to change as it passes through a given medium. And one of that is the speed, right? Imagine yourself running without anything impeding you. That is, you're able to run freely in air. But let's say you want to run in some gel, in some sticky material, that is going to actually weigh you down. And so the speed of EM waves or radiofrequency wave in a given medium is lesser than its speed in vacuum. And the ratio of that speed is what we call the refractive index. We call that the refractive index, and that refractive index is now dependent on the electrical properties of that material. Here are some of the electrical properties I've highlighted. We call the permittivity. Permittivity in this case is looking at how that material responds to the electric field in your EM waves. Imagine we're talking about it having component, the E field and the B field, that is the magnetic field disturbances. So there is a way that your material will respond to that electric field because it's the permittivity of the material. And the way the material responds to the magnetic field is what we call the permeability, that is leading to some magnetization in your material. And if there are charges, there are free charges in your material, the action of the electric field on those charges will cause them to move around. So the ability or the ease with which they move determines the conductivity, what we call the conductivity of that material. Now, these refractive index are related to those electrical properties. But for most materials, especially tissues, the magnetic permeability is essentially close to that of free space. And so largely we say that the interaction with EM waves for the human body is determined mostly by the permittivity, in this case, as shown in this relationship. Now, if we want to just a simplification, that is what we always do in physics. We try to simplify our whatever situation we are in. Let's look at the case of normal incidence where your wave is coming perpendicular to this surface. In that case, if the wave is passing through different media, say I'm going from air to glass, or I'm going from just air to the human body, an RF wave is incident normally to some on a test object, the way we are going to get the amount of intensity that is going to be reflected is based on this relationship of their refractive index. So R in this case is looking at the coefficient of reflection, and it also tells us, assuming there are no losses within your system, that there is no mechanism for dissipating the energy in the wave, we can also say that the amount of wave that will be transmitted can be given by this simple expression. All right. So for the human body, we describe the human body as a lossy dielectric. When I talk about the electrical properties of a material, another word I can use is to talk about the dielectric properties of that material. Largely, I will explain what I mean by lossy dielectric in a second. But largely, if we look at the human body, we are mostly composed of water, a lot of water, about 70% of our body is composed of water, and we have a lot of free ions moving about body tissues. We talk about sodium, calcium, potassium, all these ions crossing through the membranes, moving through the body. And so those ions give some form of conductivity to the tissue. And because we have some amount of conductivity, we say that the human tissue are not perfect dielectric. For a perfect dielectric, we don't have free charges, just like a perfect insulator does not have free charges. But because we have non-zero conductivity, when our RF wave passes through the body, some portion of it are going to be attenuated. Some portion of it are going to be lost because you have to do some work in moving these charges around. Because as these charges are moving in response to the field, they begin to bombard the atoms within the lattice of the system, in that sense, losing energy to their surrounding. And so we have some form of attenuation of the RF waves. And this attenuation is not only due to the free ions, it can also be due to the water content, because water, as we know, is a dipolar molecule. You have some hydrogens being attached to oxygen, and there is an asymmetric distribution of charges where you have towards the oxygen end is more negative and towards the hydrogen end are more positive. In that sense, you have the dipole, you're creating a dipole essentially that will respond to dielectric field. And every dipole will want to minimize their energy. That is, in that sense, they will want to align with your field. And so there is some orientational polarization in dipolar molecules that also leads to energy dissipation within our system. In that sense, it is this absorbed energy that leads to some potentially adverse biological effects that we know regarding radiofrequency wave. So this is just some equation describing the propagation of this wave. As it enters a material, it is attenuated by this attenuation constant, which has to do with the conductivity of the material. So a material that has zero conductivity is not going to have this component, but it's going to have another component that we call the phase constant. That is, there will be some change in the properties of the wave. The trajectory displayed by every point of the wave are going to slightly differ as they move through that material, say for instance, an insulator. All right, moving along. So, like we said, biological effects from these RF waves are largely due to their absorptions, but there are many factors that this absorption really depends on, besides just the electrical properties. We've talked about the electrical properties, which I put under the dielectric composition of the subject, and I'm going to talk about this in some detail. Also, we can look at the object size. That if the object size, for instance, is comparable to the wavelength of our wave, a different phenomenon results in that sense. Another complicated case would be to look at the shape of the object and the geometry of the object in respect and its orientation with respect to the incident field. A more complex case would be to look at what is the characteristic and the properties of this field in themselves as they propagate in space. Looking at the complex permittivity properties. Now, I talked about this permittivity, which is the response of a given material to the electric field. But in that permittivity is not just a constant value. It has some frequency dependence with it. That is, at DC, if you have a wave that is not changing in time, you're going to have just a component of that permittivity. Essentially, like this is properties that is explored in capacitors, right? But by the time you begin to have some variation, some changes like an oscillating signal, which is your like an electromagnetic wave, you introduce an imaginary component that leads to this dissipation, because essentially your electric field is polarizing your material, causing charges to separate, both positive and negative charges. In that sense, it's causing those charges to separate. In that sense, there is some polarization vector with respect to the electric field vector. If you're oscillating back and forth, going up and down, there needs to be some time reversal for that polarization. That is, you have your charges sloshing one way and sloshing another way. There is some mechanism of there is some form of delay in that response, and so you have some energy dissipation. So your complex permittivity in that sense depends on the frequency. That is, we're going to have a component that leads to energy storage within that material that accounts for the distribution of charges. And as these charges are moving, they are going to have some opposition because they're bombarded with electrons, they are bombarded with atoms in that material and lead to energy dissipation. So within the tissues, we have different amounts of water content. We have tissues with high water content and those with low water content, and each of these have different complex dielectric values. For instance, here we can see high water content tissues, including muscles, skin, down to the brain, and also for low content tissues, low water content tissues. And we can see the values of their relative permittivity as it varies with frequency, while their conductivity, again, especially those from the ionic component within these tissues, increasing with frequency. And these determine how energy is stored within that tissue and amount of dissipation that we experience. Now, moving on to the orientation and the size of the object with respect to the incoming electromagnetic wave. For instance, if I'm sitting watching the TV or standing in among the crowd or sleeping, the interaction of this wave with my body will depend on the object size, also as well as the shape of the object. For instance, we would not imagine the same amount of interaction with this subject as compared to a man standing or a baby sleeping. In that sense, if, for instance, there's maximum energy absorption when your object size is comparable to the wavelength of your RF field. So now, well, I showed the wavelength earlier when we started, but that wavelength is the wavelength in free space. But by the time you're propagating in the tissue, that wavelength drops, and that drops as the inverse of the square root of the dielectric constant, of the relative dielectric constant. In that sense, the wavelength of the RF wave in a test subject is lesser than that of free space. So if the object, if the tissue, for instance, that it's propagating in is comparable to the size of the RF wave, in that at that time, the energy absorbed is maximized. Also, looking at the orientation of the test subject, somebody standing this way with the electric field vector parallel to the long axis will maximize energy absorption from the RF field. Moving along. Now, we'd also say that one of the other factors that affect the coupling of RF with the human body has to do with the complexity of the incident field itself. Now, largely the physics that describe this interaction are mostly in the far field. And what do we mean by far field? Here we are looking at a wave that is very far from the source. That is, any change in the source do not affect the propagation of the wave. So the wave itself is a large number of wavelengths away from the source causing it. In this region, the electric field vector and the magnetic field vector are perpendicular, they sustain each other, and it is actually this far field that obeys the inverse square law. So the physics of the far field is well known and well characterized. However, in the near field, that is, you are really close to the source, the relationship between the electric field vector and the magnetic field vector are not well known. So we say the maximum of the E and the H field do not occur at the same point when you are really, really close to the source. And these appear to be the relevant cases at times that human subjects are exposed to. For instance, maybe near your microwave oven, you are really close to the source, or a broadcasting antenna in front of your house, and in that sense. So we are not most of the time in the far field. There are little physics describing the interaction of these waves, and for us to be able to simplify and understand the amount of energy absorbed, some form of modeling or computational simulation might be required. Okay, I know before now we have also been talking about looking at radiation dose, especially as it relates to ionizing radiation, the amount of energy deposited within the tissue per unit mass. Similarly, when we talk about radio frequency wave interaction with the human body, we also need to give a measure, a metric form of the amount of energy that is absorbed in a given mass. And that metric that we use in this characterization is known as the specific absorption rate, which is the SAR value. The SAR is defined as the power absorbed divided by mass. And that power is related to the conductivity and the scattered electric field, as well as the density of the material that the EM wave is interacting with. By scattered field here, I mean both the reflected, the transmitted, and the incident wave. Their vector sum around and in the subject is composed in this scattered field. And once we know this field, the conductivity of that tissue type, or the conductivity of that particular material we're interested in, and the density, we can calculate the amount of RF energy that is deposited within the tissue. Now, this conductivity component is composed of those of the free ion and also those due to the polarization within that material, which is frequency dependent. It can be orientational polarization and other form of polarization, either electronic, atomic, depending on the tissue type as well. Now, when this energy is absorbed, how it is seen is as a form of temperature rise, because once we already mentioned that radio frequency wave cannot ionize, what you have essentially is excitation of those electrons or those free charges from some of the material from some energy state to a higher level. At some point, the material will relax back to its equilibrium state, leading rise to energy being lost to its surroundings. In that sense, that shows up as a form of temperature rise within the material. And here is a Fourier heat diffusion equation that relates the local variation of temperature with the amount of energy that is being generated within that material or by the RF wave. And that is dependent on the thermal diffusivity of the tissue, as well as the specific heat capacity of the material. That is, this will tell me how much of heat is going to move away, how quickly heat will diffuse away from the region in which it is being generated. And this kind of analysis is very, very important, because if that heat is deposited and localized within a critical structure, then it may be dangerous. And so highly conductive tissue will conduct heat away from the points of measurement to a distant region. But one thing to note is that in this simple model, we might have neglected something, which are the other physiological processes that go on in the body. For instance, if this is generated near a tissue, a vascular structure, in that sense, you will have blood flow cooling down the region of interest in the, and you have some form of cooling processes going on that may not allow this effect to be observable in that. So now, by describing these two methods, one, we can establish the SAR value by understanding the scattered electric field around the test subject, or we look at the temperature rise. Any information, if we have one of these information, we can trace back to the amount of RF energy that is deposited within the tissue. And this leads to how the dosimetry is performed. So practically, you want to get the amount of RF wave that is absorbed within a test object. Experimentally, you design a phantom that is tissue equivalent, that is, has the same electrical and thermal property as that of tissue, and then you expose it. And one easy thing to measure is the amount of temperature rise. From there, we can solve back this equation and obtain the specific absorption rate of that particular material. Alternatively, we can measure the scattered electric field. Knowing the electrical conductivity and the density of the material, we can get our SAR value. Moving on along. Now, the main thing as medical physicists that we're also concerned with is what are the biological effects of the energy absorbed due to exposure to an RF wave. Now, in the last slide, I emphasized on the thermal effect leading to tissue heating. In extreme cases, this can be really detrimental, leading to cases of degrees of burns and maybe blindness and sterility in extreme cases. Well, also, we can have alterations in the human body that are not thermal related. For instance, if we shift some physiological set points, we can alter the body's circadian rhythm. A typical example of circadian rhythm is looking at your sleeping and waking up cycle. The interaction of an RF wave can help, modulate these normal body processes, as well as affect the immune system and even affect signal propagation within the cell membrane, because you are the ionic content of these cells are responding to the electric field. Okay, there is one other possibility, which is really an area to discuss, because, for instance, when we started this lecture, I motivated our study looking at the possibilities that people have alleged that their exposure to RF wave led to cancer. And so there has been a lot of study to look at how we can link energy absorbed from radio frequency wave to cancer cases. So right now, according to the World Health Organization, it is classified that the interaction of RF wave can possibly be carcinogenic to humans. And so this is an area of discourse. Essentially, we know from the physics that it cannot ionize any atom within the body, but we may not understand some deep molecular interactions that may be going on to affect any form of biomolecules that can, in the long run, lead to maybe a mutation in the body and eventually lead to cancer. And so this is really an area to discuss in that sense. Besides, if a test object has a medical implant, for example, a pacemaker, the interaction of RF with the subject may be different as we would have envisioned it to be. For instance, having a metal implant will co-localize the RF field and may lead to detrimental biological effect. Okay. Now, based on the safety consideration and what we understand by RF interaction with the human body, various organizations have set safety limits for the exposure, for the amount of exposure of RF wave that could lead to, that is required for most applications. And you can see here is a table from the Federal Communications Commission in the United States, looking at the amount of maximum allowed power that should be deposited within, I think this is whole body, if I'm right, for different RF frequency range in that sense. So now you can watch the unit here. In the previous slide, I show watts per kilogram, and here is just some funny unit that we can always correct back. And they are also in line with safety. You have a lot of safety sign indicating if there is an RF exposure that is beyond the safety limit that one should be aware of. Alternatively, there are various monitors that are used by those who frequently work with RF sources to be able to determine the amount of exposure that they have. Yeah. Besides, a lot of regulations, for instance, from the Federal Food and Drug Law Administration that regulates the amount of SAR that one can be exposed to, especially in medical applications. Now, because of our understanding of the physics behind the interaction of radio frequency wave with the human body, we have been able to apply them in different ways medically. One quick thing that is just logical from all our discussions so far is that we can then take an advantage of the fact that the interaction of RF wave leading to energy absorbed creates some amount of temperature rise and use that as for a therapeutical purpose. For instance, one quick application is an hyperthermia or radiofrequency ablation, tumor ablation. Now, traditionally, we know that the treatment of cancer is due to concentrating some amount of ionizing radiation like X-rays or gamma rays on a given region of interest, say the tumor. But we can also do that by concentrating high enough RF energy into a given region of interest that allows the tumor to heat up, which can lead to other biological effects such as apoptosis or even mitotic cell death. First biological response may be necrosis. That is, we have protein coagulations and all this taking place. Because, of course, as we begin to heat up the tissue, we're going to have a lot of protein denaturization in that sense. And so the RF wave have actually been applied for therapeutical purpose by hitting a region of interest. And most of this is really, really applied these days. This is in research, especially the hyperthermia aspect, where the application of some form of RF wave is given to the tumor in cancer treatment to help relax the tumor vasculature so that it can oxygen can be allowed to flow. By reoxygenating the tumor, it becomes more radiosensitive, and then ionizing radiation can be used. So this technique can also serve as an adjuvant to current treatment technique that is ongoing. All right, one other interesting application of RF wave in medicine is an area I'm very, very much interested, which is the MRI. The basics of MRI, which in previous lecture you have been exposed to, we cannot obtain any image without using radio frequency pulses. So in MRI, basically, I'm not going into the physics, but we can easily describe what is going on. You have some protons that are responding to a magnetic field that are being polarized when placed in a magnetic field, and these protons, as they try to align to the magnetic field, they do not really align, but they precess around some axis of the magnetic field. There is a frequency of precision, which is called the Lamo frequency, by which this proton precess around the axis of the magnetic field. That Lamo frequency is always in the radio frequency range. So for us to interact with those protons, we need some electromagnetic wave that is in the same frequency range, which turns out to be RF waves. And so we have to send in an RF pulse to help us to allow those precessing protons to absorb some energy and tilt them to the transverse plane, by which a signal can be measured by electromagnetic induction, according to the Faraday's principle. And so MRI images cannot be possible if we do not have an RF pulse. And so it is fundamental to our application for imaging. Also, besides these two applications, one important application is in-body communication, which a lot of interventions these days require medical implants, like one we've mentioned earlier, which is the pacemaker. You have to deliver some pulse to prompt the heart to correct any form of arrhythmia, and other applications like encephalography and the likes. And so radiofrequency waves are important, and by understanding their physics of interaction, we can apply them as we deem necessary, and other areas that are emerging from research. Okay, so briefly, I'll quickly talk about the possible areas of research that one can look into based on the understanding of the physics of RF wave interacting with the human body. One quick aspect to go into would be human body modeling, because we know that different tissue types, different tissue have different amount of water content, different ionic concentration. That is their behavior in response to RF wave becomes complex. And so therefore, a lot of research into computational modeling that allows us to treat the tissue with various architecture. That way we can be able to predict the amount of RF energy that is absorbed. For instance, we can make a simple model that allows us to calculate the whole body SAR value, or we can also define a mechanism by which we can evaluate local SAR that is deposited, because the whole body SAR may not be able to tell us how it affects other critical structures in that sense. And also an hot area or an important area of research is carrying out RF dosimetry itself, of course, which is the essence of doing the human body modeling. Well, we can also do some experimental measurements, designing some representation of tissues, and then observing the amount of energy that is deposited. Like I mentioned earlier on, some unanswered question whether RF can lead to carcinogen can be investigated when we understand more of the ways in which RF interact with the body on a molecular level, as opposed to a macroscopic description. An interesting area that I've employed in one of my research is doing electrical properties characterization. That is, we want to be able to apportion this set of dielectric constant and conductivity to some tissue types. So you want to be able to measure and to some level of accuracy that this tissue have these dielectric properties. And by knowing the dielectric properties, we are able to understand how the RF will interact with the tissue in that sense. And so there are a lot of methods that have been used. One easy method that is common is the open-ended coaxial permittivity method, where the test material is placed at the end of a probe, and the reflection coefficient within that coaxial probe changes and can be related to the complex dielectric of the material that we tend to look at. And various RF applications, like I mentioned, the MRI, the hyperthermia, and in-body communication are possible areas of research that one can look into. And that concludes my presentation and questions. Thank you.